All right. Before we start second order methods, I believe that it won't take too much time. Um, Before starting second order methods, I would like to actually address few issues. Let's get back to previous talk. Yeah. First one is on termination conditions. Wait a minute. Where am I? Yeah, somewhere here. Yeah. Yeah, like yesterday, Christian, I guess you asked about having absolute value rather than just difference. I think you're right. I was wrong in saying that it should not be a problem, but theta can actually overshoot and go to maximum. In that case, even though it's not a valid minimum, you might actually end up terminating the algorithm. So mod is very important. Thanks for that. And the here also we need to have mod. The other thing is that in a new when you are training neural network, we do gradients descending on the function f, which can be training loss. But when you're checking the termination conditions, you might do it when you have a validation set. For termination conditions, you want the validation loss to be smaller than that. So remember that here when I was presenting, I was using same F for termination conditions as well as the gradient descent. But in practicality, you might have a different function such as validation loss for terminating the algorithm. Okay, uh, is that clear? And one more thing I want to mention. What is that? Yeah, gradient descent method. Okay, I'm actually in this in this section. I'm using steepest descent descent method, same as a gradient descent. That is true only when you're using Euclidean norm. Okay. Let me explain a little bit about what I'm talking here. A general setup. So in we have function f, which is f of theta, and what we are saying is that if you are at sorry, if you are at the current state is as theta k in the ith iteration, then theta k plus 1 is equal to theta k minus plus alpha d power k. This can have a index. How did we compute in a descent direction method? This is minus gradient f of theta k by normalizing that f of, right? That is a way we defined gradient descent. This is, but when you call steepest gradient descent, you can actually allow very general metric on the space Rn. What does that mean? In steepest gradient descent, the update is the direction is defined to be argmin let's keep the index theta k inner product with S such that it's equal to 1. Here, this metric is not necessarily Euclidean metric. Let's this is Euclidean metric, and this is general metric. As we have seen the exercise in the chapter, if this general metric is Euclidean metric, then you get to see that this is indeed same as this. Okay, that's the idea. So steepest descent is defined with respect to very general metric, and the gradient descent is a special case of it. And I think it's important to mention that. So there is a question. Alpha contains the directional component. What is D? Alpha is a learning rate. Where is it? Directional component of how it is contains. The direction is given by the gradient in the gradient descent method. And alpha is just how long you want to move. That is a learning rate. What is the step size? Jade, can you clarify your question a little bit? You can unmute yourself if that is a good.
Sorry, I'm probably just misunderstanding.
Yeah.
But if alpha is defined as the negative gradient, which is normalized, so it's just moving one unit in the gradient direction, it already contains.
We are not defining the gradient, right? A gradient is a vector. Alpha is a scalar, positive scalar. And D is the directional component. D gives you.
Are you not defining alpha immediately below that as the negative gradient normalized?
This one?
Yeah.
This is the D.
Oh, sorry. I couldn't read. Sorry.
Yeah.
That makes much more sense. Thank you.
Yeah. This is the direction we take in gradient descent. So in gradient descent, we define that we always take a unit step, not unit step. The direction is unit length. Then alpha decides what is the step size. Yeah. So the method given in the notes is a special case. Yes, that's correct. The method we have given in the lecture notes is a special case of steepest gradient descent. I said it's a steepest gradient because I'm assuming that the norm we are using is Euclidean norm. That is only thing. And because when you read classical books like Boyd or something, you see this difference between these two methods, and you should not be confused there. And what else we have here? Any other questions on the previous 3 lectures? Did you guys get to go through the math part and just exercise? Because you might have some exercises where you need to apply these techniques. Yeah. If there are no questions, we can start with come on. This is it. Yeah, we're here. Okay, let's begin with second order methods. And let's go through quickly, like what is the second order approximation? It is, we have seen Taylor expansion, and if you discard higher order terms, we get a second order approximation. So let's do it one more time. for the sake of continuity. And f of theta is the function. Let's for now assume that it's a one-dimensional function. Then we know Taylor expansion that this is about Taylor expansion about some value a. It is f of a x minus a f from f of a first derivative and x minus a square by 2 second derivative at a, so on. So what we do is that we discuss this so on terms and we only take this and then we have approximation. Suppose you're an ith iteration of the descent algorithm, then you are at kth point and you want to move to k plus 1, and what you do is that you define q of theta to be f of theta k plus theta minus, I'm sorry guys, I'm using x and theta wrongly. I'm really sorry for that. And theta k, let me do it small letters. We are at this is a current point, that is where we are. Then f of, no, let's define q of theta is f of theta k plus f base of theta k. All right. If we define q of theta to be like this, then we know that in the vicinity of theta k, f of theta is actually approximately close to qt near theta k. Okay, that's the idea. And you can see that it's a quadratic equation. So essentially we are approximating around theta k with a quadratic function. That's we are denoting as a q of theta. So that's what I'm saying here. This is the second order approximation for f of theta. And if function is smooth, then it's a good approximation within very close to theta k. But if you move away from theta k, you might actually have uh, a lot of difference between f of theta and q of theta. And before saying that, let's do little bit exercise. Take your pen and ask yourself, if f of theta is this, can someone tell me, and theta k I'm taking 3. Can someone tell me second order approximation about theta k, that is 3? Quickly, can you write it down? Because we know equation, this is the equation. All you need to do is that compute first order derivative and second order derivative. Let's see who does it first. Could you show the function again? Oh, sorry. It's a theta minus 1 square and theta plus 3. It's taking longer. Did you get this theta minus 1, theta plus 5? Have you got, is that the derivative? Then what about this second derivative? 3, I guess it's, sorry, 6 theta minus 2. Is that correct? Anyone can confirm it? Guys? Okay. Once you get these expressions, what you need to do, you just need to substitute f theta k. That will be f prime of 3, and also similarly you compute f double prime of 3, and once you have, you can substitute in this expression, right? All the way, only one variable is there, that is theta, both the expressions. So you can compute approximation exactly. Now we have this first order approximation comes if you terminate this value, and if you include that, then you get the second order. Okay, that's what we have seen. So let's compare how first order and second order looks for this function. You can see that this is first order and this is second order. You can obviously know that second order is a better approximation than the first order. That's what we witness here. Okay. One thing good about second order is that it's not a straight line. It has a shape, nice shape, which has one global minimum. Further, it's a global minimum here. Okay, this is the point where the second order approximation, that is a quadratic function, which has a global minimum. Okay, this is the lowest point. So we essentially use that. How do we use that? So this is the approximation we have, and it's because it's quadratic function, it's easy to minimize this function. All you need to do is that find the derivative of uh, q of theta. Yeah, q of theta, that's what we are doing here. If you compute this, because variable is here, one is here and another one is here, there's a constant, so this has no value when you're differentiating, so this is gone, and obviously this is the term you get from derivation, and the third term gives you this second value for derivation, and you equate it to 0. And then you know that what exactly theta you need to take to get minimum. That is this one. Just rewriting these terms. Okay. So all it's suggesting that you have a gradient. It also gives a learning rate directly. If you look at this one, compare with the gradient descent thing, k plus 1 is equal to theta k. If you compare with alpha d, okay, you can see that alpha k is equal to 1 by f from theta k, and you can write f prime of theta k into this one, and d is a normalized direction, which is essentially, we know that in gradient descent we have minus, uh, Well, we are in one dimension, so let's not get confused here. It's not direction derivative, but it gives you direction here. You understand that it is directly giving us the learning rate as well as we know direction. So we can compare this with gradient descent, where there we need to find the learning rate. Here we don't need to. It specifically tells you where to go. That is what we get. If you're at theta k, and then you can see that for this particular example where you are using theta k to be 3 and the function to be this, you get theta k plus 1, the next point, to be at 1.6. Okay, you can just substitute values, because that is where the approximation, second order approximation, taking the minimum value. You come here, and this is where you come. It might not be minimum point for the actual function f of theta, but it gives you a direction. That's how you update. And again, there are termination conditions, which we discussed earlier. We can use this is in one dimension case, and obviously we can actually extend this method to higher order multi-dimensional case, just by again using the quadratic approximation. How do you do it? Recall the Taylor expansion for uh, multi-dimensional function, which looks like this. And Taylor approximation has more terms, okay, about theta k. If you write, then you have more terms. If you discard these terms, all these terms, all you get is that this one, that is what is the quadratic form we are looking for, and that we call q of theta. So it's easy, like for at least expression wise, it's easy to uh, play with. Only problem is that we have a Hessian here. It is a matrix. Hessian is just a collection of all the second order derivatives. Now, how do you do it? How do you find minimum? Again, it's a quadratic function, q of theta. So it's again easy to find a minimum value. That's by computing the gradient for q of theta and equate it to 0. What we get is that this one. Again, we have theta here. If you have inverse of Hessian, then this is the update, right? It's easy. Yeah. Again, it's if you compare with gradient descent, this one is acting like a learning rate, actually, H inverse. It's not a scalar, but that's how it acts. And the key difficulty here is taking inverse of Hessian matrix, H. Because I think yesterday someone asked, is that Rahul or someone? Rohan, I guess, about the complexity of a matrix, inverse matrix. This is a, if it is non-singular, the complexity is because it's a symmetric matrix. So there are, and this is the size of H. So to take inverse of this, the complexity is n cube, order of n cube. That's a lot. And when you are having several features in the, several variables in the neural network, then it's very difficult to actually compute this inverse. And we see what are the remedies for that issue. And under certain conditions, we are not going to talk about those conditions specifically. You can refer to the textbook I mentioned in the beginning. Okay, there is a question. Is that delta, that I mean to be delta? I'm sorry, guys. Yes, thank you, Peter. This is not G, it is Q. It's confusing because I'm using G for gradient of the actual function. This is Q. please make a note and I will correct accordingly. Okay, thank you, Peter. And so we can actually show that it has a quadratic convergence. A quadratic convergence essentially means this, that is, if theta infinite is a converging point, then at each iteration, you at least scale down by square of the, so if theta k is closer to the final point, converging point, this will be say small value 0.01. Then next iteration, you're within a distance of 0.1. That's what it says into some constant, of course. So yeah, have a look at it, but that's not very important. It works. There are issues with it. That's what we talk here. That is instability of the Newton's method. There is another question. Will the website be updated to show all the extra matter? Yes. So what happened is that we are trying to update the website. There is some issue with the synchronizing Dropbox and other things. So we couldn't do it. But immediately after the lecture, we will be able to do it. Thank you. So if you look at this, say, look at this function. Let's give an example. Okay. Suppose your function is like this, and you're being very smart, and somehow you could actually guess exactly this value, minimum value, and say this is the beginning. Okay. And sorry, this is the beginning, and this is is equal to theta optimal value. Okay. Then there is a confusion, like if derivative is also zero, then you can say that, okay, since derivative is there is zero, I can no need to worry about zero, and immediately I can actually announce that this is optimal value. But if you happen to very close to theta star, where derivative is not zero and second derivative is also not zero, but second derivative is very close to zero, then you see that you will be thrown far away from the this actual supposed to be the optimal point, because the approximation can be very far, and because derivative comes in the denominator, you'll be thrown away. And if you notice, yeah, this is the what update equation, and the second derivative is in the denominator. If it is too small, the change will be too high. That means you will be moved away from this optimal point, and method will actually take a lot of time to come back to the optimal point, and it can happen again if you end up having a similar problem. So that is one major issue. And let's illustrate some other two issues with this Newton's method. One is overshoot. Uh, okay, this is where I'm taking a function of this form, and I'm saying that I'm at theta k, which is 1.5. And I'm asking what is the next point. If you actually take time and find the second order approximation, that is what it looks like, and you can compute easily because you have a simple expression. You can compute the first order derivative and the second order derivative and expand about 1.5. Yeah, then you can actually find minimum value, that is theta k plus 1 is theta k minus, yeah, and this is 1.5. So just substitute 1.5. What you get is that theta k plus 1, which is actually 5.25. if you notice, the problem is that the next point, the function value is too high compared with where you are right now. Even though the second order approximation is actually telling you that you will go down, but that's not what can happen. So this is another issue, and you can check with many functions of the that sort. So when you are about to be closer to the minimum value, this can happen, and that will take you away from this minimum value. And again, you can actually you can take a lot of time to come back to this minimum value, if at all you come back. Thought time was being introduced. Jason, what time are you talking about?
You can hear me? It's the
Yeah,
equation. Go up a bit.
yeah. Sorry.
Yeah, that's a typo, is it? The t plus 3.
Oh yeah. Sorry. Yeah, I need to cross check. Thank you. Is that correct? Is the only problem?
Yeah, that's.
Yeah. Thank you.
I think other people said as well.
No. Thank you very much. It's my mistake. And yeah, this is clear, I hope. Any questions so far? If not, okay, let's look at the other issue with Newton's method, oscillation. Okay, consider this function, uh, which looks like symmetric around its minimum value. What happens if at all, if you happen to be at a point, say in this case, it's -1, okay? I thought of making you guys do this exercise, but let's okay. I think you can do it quickly, and again, remember that this is update. Let me write it quickly, and f prime of theta k. Yeah, and suppose theta k is -1. You can compute that. It implies theta k plus 1 is +1. Okay, so if you are here, and the second order approximation tells you that you should move to this point, theta k plus 1, when you are here. But it's not a minimum point. You are actually away from minimum point again, just as far as this distance actually. So what do? Your algorithm will again try to do the same thing and find the second order approximation at this point, and ask where is that second order approximation taking minimum point. So if I reverse the role and call this as theta k, yeah, and this is theta k plus 1, then you'll come back to the same point. So your algorithm gets stuck. It keeps moving between these 2 points. It never terminates, and it just continues to do this. So this is another problem. You can get stuck in this kind of situation. So these are the issues, and the one of the issue is that how do we do Newton's method if the second order derivative is not available in one-dimensional case? In that case, what we do is that we know from the definition that it's theta is actually limit h goes to h 0 f of theta plus h minus f of theta by h. This is the definition, right? Sorry. first order. Yeah, that is the definition of a second order derivative. So we just incorporate it, assuming that your step sizes are small enough. What we do is that we approximate second order derivative at theta k with this ratio, which looks very similar to this. Okay, this is h. It's a difference between this point and the theta, that is h. Assuming that it's very close to very small, then we can have a good approximate. And instead of earlier we have theta k plus 1, we go to theta k minus f prime of theta k by f double prime of theta. So we replace this with this ratio and we get this, and that's like a altered, modified version of Newton's method when you can't compute second order derivative. This second order secant method also can have similar problems to which we faced, we have seen earlier, and might actually take more iteration to converge than Newton's method because we are using approximation. To address some of these issues, particularly memory related, where we need to compute Hessian inverse and store Hessian, there are some methods called quasi Newton methods. And the idea is to approximate the Hessian with a different matrix. And we don't get into too many details here, but we see that we see prominent three prominent methods in the literature which are used, and we have an exercise at the end. You can go home and implement. The implementation is not very difficult, and you can see how it actually performs better than the other methods. So how do you do that? Let's recall a multidimensional case. So this is update we have. Okay, what is that? Let's for comparison purpose, this is update for quasi Newton method, but for Newton's method in multidimensional case is HK GK, right? That is what we had. Now HK inverse is actually replaced with this. QK is approximation of HK there, not alpha QK, but alpha is more of a learning parameter. If you can regulate a little bit compared with earlier method, we can regulate by including alpha. So we are including this alpha parameter learning rate in this method. And we are essentially saying that instead of taking Hessian, what we are doing, we are taking direction, descent direction to be minus QK GK and multiplying with the learning rate and adding to the theta k to get the next step. So to simplify the notation, we're just taking a gradient difference to be this and the position, location difference to be this. And that's what, once we have that, there are three ways of approximating this H inverse. That is like updating Q. We start with Q1 being identity matrix, that is ones along the diagonal, zeros everywhere of the appropriate size, that is n dimension. Then what we do in each iteration, we actually update QK as follows and just substitute into this equation. So you can quickly check that this is in fact symmetric and positive definite, if you start with, oh, this is a Q1. Q1. If you start with the Q1 being like this or any other symmetric positive definite, then you continue to be in symmetric and positive definite. That can be checked easily using this formula or this update. And particular interest is that when function itself a quadratic function, then the Q becomes A inverse. It's the same for all iterations, A inverse. When this is what we have seen in conjugate gradient methods. And so DFT becomes very similar to conjugate gradient method when you have a function which is quadratic. There is a fourth term in the first fraction is meant to be QK. Math equation 3.6. Okay. Where is it?
Yeah,
Fourth?
just in the numerator.
Yeah. This is a, sorry. Yeah.
Yeah, cool.
Yeah.
Thanks.
That's correct. Not power. So, but the problem is that again we need to store this Q and update, and that's very computationally demanding in high dimensional problems. So that we will look at in the third method. But before that, there is an alternative to this DFP method. Okay, to this update, we can actually update using this. It's more complicated expression, but it's shown to work well when you are using approximate line search, shown to be better than DFP when the alpha parameter we are learning is actually we're learning using approximate line search, which we discussed earlier. And however, again, the storing is again a challenging task in high dimension problems. That's what we address in the third approach. It's called limited memory BFGS. This is it is a modification to the previous method. Instead of actually storing QKs and updating them, it does a clever way. There are two steps here: backward procedure and forward procedure. In the backward procedure, we compute something called vectors, a sequence of vectors using. Okay, let me recall these two definitions. We have a gradient difference, a sequence of gradient difference, which comes from previous iterations, a sequence of position difference, a location difference, that the delta theta. Okay, so these are available. And what in limited memory BFGS, what we do is that we store last M, you fix M, and we store last M gradient difference vectors and position difference vectors. Okay, that's what we store. Once we have access to them, we actually take gradient wherever you are. Suppose you are at theta k in the kth iteration. So you take QM being f of theta k. That's easy to compute, and we already compute that for approximating the function. And recursively go back from m-1 to 1 and compute qi. It's a backward using only gradient difference and the location difference. Once we have this sequence and you go m steps backward, and you construct certain vectors in the forward direction, The math part is complicated. I'm skipping intentionally because no, this course is not meant to understand what is the math behind, but the procedure is important to understand. Once you have backward procedure, you have a sequence q of 1 to q of m. We constructed in this direction. Now we construct another sequence of vectors m z up to m in this direction, and that is constructed by initiating z0 to be this and updating. Finally, once you compute zm, that is a negative of that one becomes the descent direction. So what is the update then? K plus 1. So theta, final update will be theta k plus 1 is equal to theta k minus, or say alpha k, and dk. Dk is essentially given here. I'm just I just eliminated superscript k because it's the same procedure happening in every iteration. And alpha k, once you have direction, alpha can be computed using approximate line search, which we have seen. And yeah, finally, just go home and take this function, Rosenbrook function, which we used earlier, start from any initial state and develop these methods, and you see that they work pretty well, and compare them with the other methods where code is available. All right. I think that's about this chapter, and I'm happy to take questions if you have any. Property 2, I guess this is the one, right? Yeah. Yeah. So it takes some time to actually find out if function is quadratic. You already have a quadratic approximation. So then what is Hessian? Hessian actually A itself. And if you actually write Q in this thing, if you update, you notice that the approximation itself becomes A inverse. By the way, I need to mention that for quadratic function, you start Q of 1 to be H itself, that is A, right? Once you start with, the recurrence will not change Q value, and you end up seeing Q being A inverse in each iteration. Is that making sense? You just need,
clarify,
yeah, you just need to,
whether Q was updating or whether it was staying the same, but that makes sense now. Thank you.
yeah. So just look at expression and you play with it, you see that in the notes that I open via the link of Canva. Yeah, so Alex, I mentioned just now that there was some issue with updating chapter notes in the morning. I'm going to change it, and I'm going to update all this thing. Yeah, because there is a question about why secant method. Oh, come on. Yeah. Secant method takes more iteration than for convergence than Newton's method, because think about a quadratic function, okay? In quadratic function, we know that Newton's method takes only one step because it's already in quadratic form and we are not discarding any terms. And so whatever minimum is for quadratic function is a minimum for the actual function also. So it takes in one step. But because we are approximating second derivative with this quantity, we are not at the minimum. So it will take more steps even in that simple case. Now, similarly, we can actually expect this to happen even for non-quadratic functions. Does it make sense? Is it clear? I can explain if that's not clear.
But in the second order method, Newton's method also take the second derivative, right?
This one?
Yeah, yes.
Yeah, it takes second derivative, Newton's method. And in secant method, we don't take second derivative, we approximate it.
Yeah.
Is that the yeah?
Yes.
We
Yes.
approximate it. Yeah.
So in the second method, we do not calculate the second derivative. And in the
In
Newton
second method, we don't calculate second derivative. Instead, we approximate it and just substitute in this update.
Okay, thank you.
Yeah, because if you notice, it has only derivative terms. Only one issue is that we need to have 2 points decided before starting the algorithm, because generally we need theta 1, but here we need theta 0 also. And that we take around theta 1 somewhere closer. Yeah, because otherwise we won't be having this expression computed at first iteration. That's good. Any other questions?
Well, sorry, I have a question. Will you update the solution of the exercise?
These are simple exercises. I really happy to discuss directly in consultation, but it should be easy to actually solve these exercises. And if you have any doubt, please come to consultation hour and I will clarify.
Okay, thank you.
Yeah. No other questions? I think we are good to go. This is this last lecture. We're done with optimization part. I'm happy to hear if you have any suggestions or feedback on this, and I'll be seeing you guys again next time.
Thanks, Sarat.
Thank you. Thank you, Benoit.
My turn tomorrow.
You'll be there, right, tomorrow?
Yes, tomorrow. Everyone, you have all the slides I'm going through for 3 hours on the website, and you have the slide and some HTML file just to show you some code running for some specific topics. So you can download all of this on the website. Yoni, I've put this on the website.
Yeah. Yeah. Make note of that. Yeah. Yep. Thank you, Benoit. Okay. Time to go. All the best, guys.